So for our last class in Math 150, we're going to talk about linear regression. And here's what linear regression tells us. We learned this idea that you can draw a bunch of ordered pairs on a Cartesian plane. And we learned that sometimes these ordered pairs are closely related to each other, right? We have strong correlation coefficients. And we learned that sometimes we can get a cloud which doesn't give us much information at all. It tells us that these two variables are not related at all. So with linear regression, that's going to help us find what we call the equation for best fit. So that is, if you have a bunch of ordered pairs, there is one line that you can draw through that captures most of the ordered pairs on the line and that minimizes the distance from the ordered pairs that are not on the line to the actual line itself. And that's what we call a regression equation. So we're going to speak about linear regression. That is, if you have a scatter plot, how can you find the equation for the line that gives you the best fit? And when you can use regression equations, so at some point, I mean, you can draw a line through anything, but at some point it's not going to give you any information, and what linear regression is useful for. So I want to spend a few minutes taking you back to algebra, where you spent some time talking about the general equation of a line, and that is the line y equals mx plus b. Y equals mx plus b is a line that's in slope-intercept form of a line. The reason we call it slope-intercept form of a line is, remember that this m guy over here, this tells us what the slope of the line is, and you guys may have learned slope of the line as being rise over run, so how to get from one point on the line to anywhere else on the line. And we also have this b value over here, and this b value tells us what the y-intercept of the line is. So the idea is, given any equation of a line that's in that form, y is equal to something times x plus or minus something else, that we can graph it with general ease. So let's take a look at this line, y is equal to 2/3 x minus 5, and make sure that you're comfortable graphing it. Let me put some little ticks on the line over here. There's 1, 2, 3, 4, 5. There's some more ticks on the line, 1, 2, 3, 4, 5. There's some more ticks. This is 0, where these two guys meet. There's -1, -2, -3, -4, -5. And here's these guys, -1, -2, -3, -4, -5. So the equation of the line, y is equal to 2/3 x minus 5, has a y-intercept, so specifically it's a y-intercept at -5, which means we're hitting at -5 on the y-axis, and it has a slope of 2/3, which means to get from one ordered pair to any other ordered pair on the line, we're going to rise 2 units and go to the right 3 units. And slope is constant if you have something that's linear. From one point to any other point, that motion, that up 2 over 3, is going to be the same on this line. So if I start here at -5, I go up 2, that's going to take me to -3. I'm going to go over 1, 2, 3, and that's going to plot me right here at the ordered pair 3, -3. To finish it, here's the fun part, we just draw a line through it. Now again, that's if we have the lines in the form y equals mx plus b. Y is our y-intercept, so it's where we're hitting on the y-axis, which is this guy right over here. And m is our slope. That's the movement that takes us, that is here, we had a slope of 2/3, so we went up 2 units, and then over 1, 2, 3 units to hit that second point, or to get that other ordered pair that's on the line, which is 3, -3. In statistics, if we had paired sample data, so paired sample data, so that means we're dealing with the sample, and we have paired data, so x1, y1, x2, y2, x3, y3, whatever it is, we have a bunch of ordered pairs that come from a sample all the way up to xn, yn. Then the regression line is the straight line that best fits the scatter plot of the data. And the regression equation looks like this. It looks like y hat equals b naught plus b1x. Now, I want to compare that with what we just talked about, and what are the difference between the algebraic equation of a line and what's the difference between the statistical equation for a line. So algebraically, the line y equals mx plus b has a slope of m. Now the slope is the number that's attached to x. Notice attached to x over here, we have a b1. So b1 represents the slope of the regression line. In algebraic form, we call the y-intercept b. Okay? Notice that that's the constant term, that's a free-floating constant term. In statistical form, that free-floating constant term over here is B naught. So this B naught represents the y-intercept, and this B1 represents the slope of the line. So one more time, if we're talking about the general equation of a line algebraically, we call it y equals mx plus b. If we talk about the general equation of a line, statistically speaking, we call it y hat equals b naught plus b1x. Now y hat, we refer to y as being the response or dependent variable, and x we refer to as being the explanatory or independent variable. So x is what's used to explain y. So temperature means more ice cream. Studying harder means better final exam grade. Getting enough sleep the day before a marathon means running at a better pace. So x is what we call the explanatory or independent variable, and we use x to help us explain what y is, to help us explain our outcome. Now, if instead of dealing with the sample, if we're dealing with the population, then we use the equation y hat is equal to beta naught plus beta 1x. And we talked about this before in the semester, that if you tend to have Greek letters, and this is the second letter of the Greek alphabet, it's also called beta. If you have Greek letters, then that means we're dealing with the population. So all this is telling us is this is the regression equation if we're dealing with the population. And the regression equation, if we're dealing with the sample, we're just going to use the English alphabet. That's what we use. Y hat is equal to b naught plus b1x. So sample, it looks like this. Population, it looks like this. The only difference are the variables represented by the slope and the y-intercept. One's beta and one's b. So I had something in mind for this temperature and sales chart, but then I didn't like it, so I'm not going to talk to you about it. But what I want you to know is that we're not going to worry about any of this information over here. What I want you to know is we can draw a picture of the line for the line of best fit. And what that picture does, and here what we're going to do is we're going to talk about how to estimate drawing a picture, and then we're going to find the equation for the line of best fit, how we can find the exact equation for the line of best fit. But to estimate the line of best fit, let's take a look at this bit. And again, don't worry about any of this over here. There are literally an infinite amount of lines that we can draw in this little rectangle over here. But the line of best fit does the following. It captures most of the data. It makes sure that whatever data isn't captured in it, that data gets a lot of ordered pairs on it that are fairly close and not too far away from it. So let's take a look at these. I hope you can see that none of these are great representatives of it. This line over here, this kind of goes parallel to the data but doesn't capture any of the points on it, even though this is fairly linear. Same thing with this red line. Now we captured 1 or 2 points on it, but look how far away these guys are from it. We have a lot of points that are underneath it, right? We have this one point that's a little bit above it, but most of these points over here are underneath it. So let me get rid of these guys. Not a good line, not a good line. Let me see if I can get away with just erasing these little pieces over here. The black line and the red line. The black line again captures 2 pieces of the data, but look at all the ordered pairs that are away from it. And the red line, same thing, it captures some more of the data, but it's missing this big chunk of data over here. So I'm going to draw, and I hope you can see when I draw it, why this could be the best line of fit. Let's do this. Let's take a look at these shapes. Let's take a look at this guy. And I'm going to start right here. I'm going to try to capture as much of the data as I can. I'm using technology a little bit here, and boom. This looks like a good line of best fit. Why? Well, look, first of all, I hit 1, 2, 3, 4, 5, 6 of the ordered pairs on that line. The ordered pairs that are off of it aren't too far away from it, right? This guy's pretty far away, but everything else has a minimal distance to get from that point to the line. So there is one line that represents what we call the line of fit, the best line of fit. And this line that I just drew would represent that line. Now let's take a look at this guy. It says, let's use the equation to estimate. So instead of the equation, I want to see if you can use the line of fit the line of best fit, to estimate the number of sales when the temperature is 21 degrees Celsius. So what that means is I'm going to use my line. I'm going to go up here to 21 degrees. Here's 21 degrees on that line. And if I wanted a good estimate, I can interpolate the data here and figure out that a good estimate, so when my X value is 21, it looks like my Y value is, let's say, what do we say, around $460. So it gives us a good idea as to what some of the other ordered pairs would look like that aren't necessarily on this line, but we can come up with a good estimate as to what those values would be. So based on the data set of coordinates, there is a single best line of fit. We estimated the line of best fit above by eyeballing the data, just by drawing a bunch of lines until we figured out what was the best line that could fit with that data. However, we can use a formula to actually find the exact values of the slope and the y-intercept for the line of best fit. So that is this line that I just drew above. This line has an equation that goes hand in hand with it. So if we were to extend this over here, we could figure out what the y-intercept of this line is. Now this is not the y-intercept. The y-intercept is when x is 0, so we would have to extend this guy back a bunch and figure out about what that value was when y was 0. So that would be our y-intercept. And then we could figure out what the slope of this line is by finding any 2 points that are on the line. And that would give us a general idea as to what the equation for this line was that we just eyeballed. Now let's figure out how to find the equation of the line for the line of best fit. So remember that the formula is y hat is equal to, go back up here and find the formula, b naught plus b1x. So y hat is equal to b naught plus b1x. So if we need to find the formula, so we're going to fill in the slope, figure out what that slope is, and figure out what that y-intercept is, figure out what b1 is, and figure out what b naught is. If we need to find the formula for the line of best fit, the first thing that we're going to do is we're going to find b1, or we're going to find the slope. And here's how we find b1. We're going to use this equation, n times sum xy minus sum x times sum y, divided by n times sum x squared minus sum x quantity squared. Now, in regards to what the n's, x, and y's mean, these should look familiar because we talked about these when we were looking at Pearson's moment correlation coefficient. N represents our sample size, how many ordered pairs we have. X represents the explanatory variable, first variable in the ordered pair, and y represents the response variable. So the first thing we're going to do is we're going to find the slope, or b1. And then we can literally just plug that number in. The second thing that we're going to do is we're going to find the y-intercept. So we can use the following formula to find the y-intercepts. And remember that the regression equation looks like this. Y is equal to b naught plus b1x. We're going to start off and find the slope first. When we're done finding the slope, then we're going to find the y-intercept. And we find the y-intercept by running it through the formula y hat minus b1x. Y hat represents the mean of the y values. Okay, so you add the y values and divide by how many there are. Minus b1, which is the slope, times x hat, and x hat represents the mean of the x values, or the explanatory variable. So let's do this. I want to make sure that you guys are comfortable with how to actually figure out what this process looks like, and let's take a look at this example. And we did do this example already when we were looking at the correlation coefficient, but now I want us to take it a step further, and I want us to find the equation for the line of best fit based on the information above. Okay, so we have a sample, right? We pulled off 8 crickets. We counted the amount of times that they chirped per minute, and we recorded the temperature. So this is a sample. So we're going to use this formula. And remember, the first thing that we want to do is we want to find B1, or we want to find the slope. So the formula for slope, or the formula for B1, looks like this. I'm just going to copy and paste this down here. Oops, sorry about that. So the formula for slope looks like n times sum xy minus sum x times sum y divided by n times sum x squared minus sum x quantity squared. So we're going to do exactly the same thing that we did when we were dealing with the column method before. I'm going to write down my x values. I'm going to write down my y values. All right, I'm going to have a column, sorry, I'm going to have a column for my x values, a column for my y values, a column for my x times y values. And then we don't need to have a column for y squared. Then we're just going to have a column for x squared. Okay, x values. So I'm just going to read these 8 ordered pairs up here. 55, 67, 75, 99, 119, 134, 149, 178. Okay, and then the y values that are associated with them, make sure that you put them next to each other. It's important for that third column. 50, 54, 55, 60, 67, 69, 74, 79. Okay, so at the bottom of these guys, remember at the bottom of these columns represent the sums of these. So let's do the sums of the x values first. And you can use, if you need to figure out the Pearson's moment correlation coefficient, because it's the same data, you can literally just pull those values off of here. So we have 55 plus 67 plus 75 plus 99 plus 119 plus 134 plus 149 plus 178. And we get 876. I'm going to check my work for this too, because I believe I've been making some computational mistakes. So minus 178, minus 149. Okay, that looks good. Now let's do the same thing for the y's. So we're going to sum up my y column. I have 50 plus 54 plus 55 plus 60. Plus 67, plus 69, plus 74, plus 79. And it looks like I get 508 for these guys. And again, let me just double check. Okay, 50, 54, 55, 60, 67, 69, 74, 79, 508 looks good for that one. Okay, so the next column is going to be XY. So we're just going to multiply the coordinates together, multiply these two together and record it over here. So 55 times 50 equals 2,750. 67 times 54 equals 3,618. 75 times 55, 4,125. 99 times 60, 5,940. 119 times 67, 7,973. 134 times 69, 9,246. 149 times 74, 11,026. 178 times 79, 14,062. Okay, and now I'm going to sum all these guys together because we need it for this bit. So 14,062 plus 11,026 plus 9,246 plus 7,973 plus 5,940 plus 4,125 plus 3,618 plus 2,750. And I get 58,740. Let me write that in there, 58,740. Okay, and then one more column, just x squared. So we're going to take each one of these values and square it and put it in this column over here. So 55 squared, 3,025. 67 squared, 4,489. 75 squared, 5,625. 99 squared. 9,801. 119 squared. 14,161. 134 squared. 17,956. 149 squared. 22,201. And 178 squared. It's 31,684. Okay, let me add these guys together. Let's see what we get. And it's going to take me a little bit to do this, so please feel free to do this on your calculator as I'm working on this. I get 108,942. I'm going to double check my work though. 108,942. I wish I could see that. 948 too. Okay, give me 1 second. All right, looks good. Okay, so we have what we need for us to figure out what B1 is, or for us to figure out what the slope of this line is. I'm going to plug in these values. And so n, remember n represents the number of ordered pairs, and we have 1, 2, 3, 4, 5, 6, 7, 8, so n is 8. Times sum xy, well, 58,740. Minus sum x, which is 876. Times sum y, which is 508. Okay, divided by n, which is 8, times sum of x squared, times it's 108,942, minus sum of x, which is 876, quantity squared, so we're squaring it. Okay, so I'm going to do the numerator first, and then I'll do the denominator, and we'll come up with a good approximation for the slope. So we have 8 times 58,740 minus 876 times 508. Let me just double check my math. And I get 24,912. And the denominator, 8 times 108,942 minus 876 squared, I get 104,160. And now I'm going to divide the two, so 24,912 divided by 104,160, and I get 0.23917. 0.23917. Okay, so this is what we know so far. Y hat is equal to B naught plus, we just found B1, right? That's the information we just found. We just found B1 plus 0.23917x. But the equation of a line, we need two things. We need the slope and we need the y-intercept. So the next thing that we're going to do now is we're going to focus on how we find b naught, or how we find the y-intercept. So let's go back and look at the formula for the y-intercept. So the formula for the y-intercept is this. Okay, so this is the formula for the y-intercept. And it tells us the y-intercept is equal to y hat minus b1 times x. So, okay, so y hat. Y hat represents the mean of the y values. So we're going to add up all of these y values. Remember that we let the temperature represent the y values. And then we're going to divide by 8 because that's how many there are. So it's the mean of the y values. So I'm going to add all these guys together. Now, actually, interestingly, we already know what the sum of the y values are, right? we know that from this formula over here. We found the y's and the sum of the y's. So we're just going to take 508 and we're going to divide that by 8, and we get 63.5 minus B1, which is the slope. That's what we just found here. So we'll do 0.23917 times x hat, and x hat represents the mean of the x's. Y hat represents the mean of the y's. Okay, so the mean of the x's, again, we're going to add up all the x's and divide by however many there are. We already added up the x's. We did that right here in this column. So we're going to do 876 divided by, and we have 8 values, so divide that by 8, and that gives us 109.5. Oh. Excuse this notation over here. This shouldn't say this. This should say B naught. Sorry, B naught equals, this is y hat minus B1 times x hat. Okay, so B naught represents our Y-intercept. Okay, so B naught is 63.5 minus 0.23917 times 109.5, and we get 37.311, rounded to 3 decimal places. So B naught equals 37.311. So in terms of the regression equation, this is the regression equation. We just have to plug in for B naught. The regression equation is y hat is equal to B naught, which is what we just found, 37.311, plus the slope, which is 0.23917, and x. So it's going to stay here as x. So if we want to find information about this line, x represents the chirps per minute, and y represents the temperature. So if we substitute any value in for x, if we substitute in the chirps per minute, and we substitute it in this formula, that will tell us approximately what the temperature is. And vice versa, if we substitute the temperature in for y, we can figure out about how many chirps per minute we should have based on that temperature. So you can use these formulas to help you predict information as long as it's within a decent range of your data. Let's do that for this next example. Use the equation above to predict the temperature for cricket chirps 140 times per minute. So we have y hat is equal to 37.311 plus 0.23917x. Now remember, this is cricket chirps, and we know from above that cricket chirps is represented by our x value. So what we're doing here is we're saying take that equation, substitute in for x 140, and let's see what we get for y hat, or let's see what we get for the temperature. So we're going to substitute in 37.311 plus 0.23917 times 140, and we get 70.7948. So this information is telling us if we have 140 chirps per minute, the temperature is around 71 degrees. If we have 140 chirps per minute, so think about if you were to stick 140 right in here, it's in between 130 and 149, 71 is within that range. It's well within that range over there. So it makes sense. Now, I can't ask you something like something crazy, like if a cricket, or if the temperature is 400 degrees Fahrenheit, how many times does a cricket chirp per minute? And the reason why is because 140 degrees Fahrenheit, everybody's dead, the crickets are all dead. So we'll get an answer, but the crickets are dead because it's so hot outside. We'll get an answer, but it's not going to make sense. So you just have to make sure that you're within your scope of data. You can do a few value points outside of it, but not too many. So that is, you know, we could do like 81 or 82 degrees. This trend will continue for a little bit, but we can't be sure that this line is going to be linear all the way across. And in fact, like I said before, at a certain point, the crickets just stop chirping because they all die off. So we don't chirp anymore. Okay, so let's do this. I want to make sure that we end with one more example, and I want to make sure that you're comfortable with these two formulas. So this last example looks like the following. A chart relating the number of years of education after high school and the average salary in 2020 of 6 people follows. So this is a chart. And what this does is it tells us the average salary of people with years of education after high school. So somebody that has 2 years of education after high school makes on average $45,000 a year. Somebody that has 3 years makes on average $37,500. Somebody with 4 years makes on average $52,000. Somebody with 6 years makes on average $65,000, 10 years makes on average $72,000, and 12 years makes on average $68,400. So I want us to end with, first of all, let's make sure that we're comfortable sketching a scatter plot with this information. And we're going to let X represent the number of years of education after high school. So number of years ed. I'm going to let Y represent the salary. I hope you can see that this is definitely a sample because we only have 6 things here. For our x-axis, we're going from 2 to 12, so we could just do it by 2s. We could do 2, 4, 6, 8, 8, 10, 12. For our y values, we have a minimum at 37,000. We have a maximum at 42,000. So I'm going to do this. Remember, we're not starting at 0. Let's start at, I don't know, 35,000. And then we can go up in terms of 5,000s, 40,000, 45, 50, 55,000, 60,000, 65,000, and we're going to end up over here at 70,000. Again, it's up to you when you scale it. Your correlation coefficient, I mean, as long as you scale it as long as you scale it as appropriately as possible, you know, you could use 3s over here, you could use 5s over here. It's okay. It shouldn't vary too much, and just try to keep the width of each one of these equidistant apart. Okay, so let's scatter plot this guy. Somebody with 2 years of education spends, or is making 2 years of education after college is making $45,000 a year. Somebody with 3 years of education is making $37,500. So let's put this guy right here. Somebody with 4 years of education is making 42. Somebody with 6 years of education is making 65. Somebody with 665. Somebody with 10 years of education is making 72, so we're a little bit above 70. And then somebody with 12 years is making 68.4, so right around here. Okay, so here's a scatter plot. Let's talk about how we can find, we can go back, we can find our, let's talk about how we can find the correlation coefficient that goes hand in hand with this. First of all, a good estimate of R. I would say if I had to estimate R, first of all, we know that R is going to be positive. These guys are kind of scattered apart, not too close, not too linear. So I would say I would give R maybe 0.65. So there is definitely some correlation between number of years of college after high school and salary. But let's actually find, and again, this is my approximation just looking at it, let's actually find R. So I'm going to make you a little nauseous. I'm going to zoom back up to the top of this guy. And I'm going to take a quick snapshot. Here we go. I want to get this formula for R here. Copy it, and let's paste it down here. And let's find R. Okay, so R is equal to n times sum xy minus sum x times sum y divided by the square root of n times sum x squared minus sum x quantity squared, n times sum y squared minus sum y quantity squared. So we have 1, 2, 3, 4, 5, 6 ordered pairs. Here's x. I'm going to make y pretty thick because we're dealing with some pretty big numbers over here. Same thing with xy. And then we'll do x squared. Doesn't matter where you do it as long as you put it in. X squared is going to be kind of small. Y squared is going to be pretty big. So let me give y squared this fat space over here. So let's start with x. For x, we have 2, 3, 4, 6, 10, 12. The y's that go hand in hand with that. So it's 45,000, 37,500, 52,000. Goes with 4, 65,000 goes with 6, 72,000 goes with 10, and with 12, 68,400. Now I'm going to keep these formulas up here because not only when we're done finding R, I just wanted to do a little bit of review to make sure that you're comfortable finding the correlation coefficient. But you'll see we're going to use a lot of these values when we talk about finding the line of best fit as well. So these two are intrinsically tied together. Let me find the sum. I'll put the sum of these guys on the bottom over here. Let's see if I can take this guy and just move that down a little bit, add a little bit more space. Can I move you down? Are you going to be happy with me if I move you down? Okay, we can do this. Let's do this. Can I just pick you up and move you? Oh, you're not happy with it, are you? Oh, there we go. Okay, let me move this guy down too. Okay. Sorry, you're good. Okay, so the sum of these values are going to go over here. Let's do the sum of the x's first. 2, 3, 4, 6, 10, 12. And then we get 37. Let's do the sum of the y's next. 45,000, 37,500, 52,000, 65,000, 72,000, 68,400, 339,900. Okay, x squared for this column. Again, I'm doing it in a weird order. It's okay. So 2 squared, 3 squared, 4 squared, 6 squared, 10 squared, 12 squared. Let's find the sum of these guys. 144 plus 100 plus 36 plus 16 plus 9 plus 4, 309. XY, so now we're going to multiply these two guys together, record it over here, and then write down their sum. So 2 times 45,000 is 90,000. 3 times 37,500 is 112,500. 4 times 52,000 is 208,000. 6 times 65,000 is 390,000. 10 times 72,000 is 720,000. 12 times 68,400, 820,800. Okay, now let me add up these values. Okay. I get 2,341,300. I told you it's a big number. 2,341,300. And let me just do this next. Let me double check my math here to make sure these numbers are okay. 820,800 minus 720,000 minus 390,000 minus 208,000 minus 112,500. And 90. Okay, so those numbers look good. Okay, so this last chart over here, for this last guy, we're going to take each one of these y values and square it. Again, these are going to be huge. So let's do 45,000 squared. Oh, yeah. 2 million, 2 billion, 25 million. Sorry, guys, big numbers. Yes. 37,500 squared. Let me check 45,000 squared one more time. Hold on. Yeah, 2,025,000,000. Okay, oh, 37,500. 37,500 squared. 1 million. 1 billion, sorry, 406 million. Keep doing that. 250,000. 52,000 squared. 2,704,000,000. 65,000 squared. 4,225,000,000. Sorry. 72,000 squared. 5,184,000,000. And last one, 68,400 squared. Oh, 4,678,560,000. All right, now I'm just going to sum these numbers up. Make sure you type these very carefully into your calculator. 1, 2, 3 plus 4, 2, 2, 5. 1, 2, 3, 1, 2, 3 plus 2, 7, 0, 4. 1, 2, 3, 1, 2, 3 plus 1, 4, 0, 6, 2, 5, 0, 1, 2, 3 plus 2, 0, 2, 5, 1, 2, 3, 4, 5, 6. Ah! Okay, and we get 2, 0, 2, 2, 2, 8, 1, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And we get, give me a second. That does not look right. Hold on. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. How many zeros we need to put here? Times 10, then 10. Hold on one more second. 1, 2, 3, 4, 5, 6, and then 4 zeros. 1, 2, 3, 4. 2 trillion. 2. Let me do that one more time. Sorry, guys. I want to make sure that we get this number down okay when I'm adding these together. My calculator is not happy with these. Okay, one more time. I'm going to add them up. 2, 0, 2, 5, 1, 2, 3, 4, 5, 6 plus 1, 4, 0, 6, 2, 5, 0. 1, 2, 3 plus 2, 7, 0, 4. 1, 2, 3, 4, 5, 6 plus 4, 2, 2, 5. 1, 2, 3, 4, 5, 6 plus 5. There we go. 5, 1, 8, 4. 1, 2, 3, 4, 5, 6 plus 4, 6, 7, 8, 5, 6, 0. 1, 2, 3 equals. Get the same thing I got before, which is good news. So I get 2.022281 times 10 to the 10th power. Times 10 to the 10th power means I'm going to pick up this decimal and move it 10 places to the right. So 1, 2, 3, 4, 5, 6, and then I have to tack 4 zeros on there. So boom, kaboom, kaboom. That's, oh, okay, so that's what happened. I am just going to double check my math. Give me one more second, and I appreciate you being patient with me. I just want to make sure I don't steer you down the wrong path. Minus 5,184,000,000 minus 4,225,000,000,000,2,704 is 1,406,250,000 equals. All right, we're there. That's what it's equal to. Oof, look at that giant mess. All right. So that's as sloppy as it's going to get. Now we're going to be able to substitute things in and make it look a lot nicer. So for Pearson's correlation coefficient, and we are going to use these numbers again, we're not all doing this for naught, so don't worry about it. N represents the number of ordered pairs that we have, and we have 6 ordered pairs, times sum xy, so here's sum xy, 2,341,300, minus sum x, which is 37, times sum y, which is 339,900. So this is the numerator for our correlation coefficient. Let's figure out what we get. I'm going to type this right into my calculator. 6 times 2,341,300 minus 37 times 339,900, and we get 1,471,500. Okay, denominator. Let's figure out what the denominator is. I'm just going to double check my math. I'm going to double check my math on everything here because these numbers are big. I didn't even think about the largeness of the numbers. That one looks good. Okay, denominator. Lucky that we have computers that can figure out the correlation coefficient in about 0.35 seconds. N, once again, it's 6. Sum of x quantity squared is 309 minus sum of x quantity squared, so this is minus 37 squared. Okay, that's the first bit, times n, which is 6. Sum y squared is that big ass number. Minus sum y quantity squared, so this guy. Sorry, let's do this and let's do that. Okay, so I'm going to do this step by step. I'm going to first figure out what this quantity is equal to over here. 6 times 309 minus 37 squared. That gives us 485. Times, so it's this bit times this. I'm going to do 6 times 20,222,810,000 minus 339,900 squared. And I get this. 5,804,850,000. Okay, so now, and again, I'm going to come back up to this in 1 second. Sorry about that. So now I'm going to take the square root of these two, and I'm going to write down that answer in the denominator here. So the square root of 485 times 5,804,850,000. And I get this guy. 1,677,901.144. We're almost there, we're almost there. Okay, so the quotient of these two, when we divide these two, these tell us what Pearson's correlation coefficient is, 1471500. I'm going to divide that by 1,677,901.144, and I get 0.877. Okay, so the correlation coefficient was a little bit higher than what I initially anticipated. I said it was 0.65, but it's really 0.877. All right, and so that's the correlation coefficient that we would use. So there is a pretty decent correlation between the number of years of education after high school and the salary according to this. But the last thing that I wanted to focus on was making sure that you're comfortable with finding the equation for the line of best fit. And again, we're going to use a lot of that information that we just talked about to help us out with this. So let's make sure you can find the equation for the line of best fit. Remember that the equation for the line of best fit, y hat, is equal to b naught plus b1x. The first thing we're going to do is we're going to find b1. b1 is equal to I'm just going to copy the formula for B1. Okay, so B1 is equal to n times some xy minus some x times some y. And B1 is equal to, so let's just start plugging this information in. N, well again, in regards to this information above, we know that we have 6 ordered pairs, so we're going to call it 6. Now this should look familiar, some xy minus some x times some y. And if you notice, this is exactly the same thing as the numerator for the correlation coefficient. So the slope, the numerator of the slope, and the numerator of the correlation coefficient are the same thing. So n times some xy, so 6 times, and here are the values over here, some xy, 2,341,300. Minus some x times some y. Some x, right here, the sum of our x's, it's 37. Here's some x, here's 37. Times some y, well, the sum of our y values, these guys here, 339,900. Okay, in our denominator, well, actually, let's simplify that down to a single value. We have 6 times 2,341,300 minus 37 times 339,900. We already know what we're going to get. We're going to get 1,471,500. And again, it's the same value that we got over here when we were dealing with the correlation coefficient. So again, the numerator of the correlation coefficient is exactly the same as the numerator for the slope. Now the denominator, you'll see the denominator should look familiar too. So that this value over here in the denominator is just this first value over here for Pearson's moment correlation coefficient. So it's just, in terms of simplifying it, it's just this guy right over here. So it's n times some x squared minus some x quantity squared. So n is 6. Times some x squared. Well, our some x squared term is this guy over here times 309. Minus some x quantity squared. And some x quantity squared is going to give us 37 squared. Okay, so 6 times 309 minus 37 squared gives us 485. So this is the slope of this line. And when we divide the two, 1471500 divided by 485, we get 3 million. I'm going to round to 2 decimal places here. Sorry, we get 3,034.02. Okay, so far in the equation of the line, this is the information we have. We have y hat is equal to b naught plus 3,034.02 times x. We just figured out what b1 is. This is the slope of our line. But after we're done finding the slope of the line, now we have to go back and find the y-intercept. So now we have to find b naught. And the formula for b naught, let me go back up here and get the formula for b naught. The formula for b naught is y hat minus b1 times x hat. Now remember that y hat and x hat mean we're dealing with the mean of the y values and then the mean of the x values. So let's go back up here and figure out what y hat and x hat are. Okay, so x hat means we're just going to take the sum of our x values and divide by however many there are. It's the mean of the x values. So we know that our x values sum to 37, and 37 divided by 6, because we have 6 x values, gives us 6.167. So x hat gives us 6.167 rounded to 3 decimal places. Y hat means the mean of all of our y values. And again, to figure out what that is, well, we're going to go to sum of all of our y's and then divide by 6, and that will tell us what the mean is. So we have 339,900, divide that by 6, and we get 56,650. $56,650. So the formula to figure out what the y-intercept is, it's equal to y hat, which is 56,650, minus B1, and we figured out what B1 was right over here. It's 3,034.02 times x hat, and here's x hat, 6.167, so times 6.167. Oh, sorry about that. Okay, so let's figure out what value we get for B naught. 56,650 minus 3,034.02 times 6.167, and we get, rounded to 3 decimal places, 37,939.199. So that's our B naught, and that's the value we're going to substitute back in right over here. So the regression line for this sample is B naught, which is 37,939.199, plus M, which is 3,034.02 times X. This is the equation, or the regression equation of the line. So if we were to draw a line that best fits this data over here, that would be the equation of the line that best fits the data. And you can see, take a look, our y-intercept is right around, I think we said in the equation of the line that we have a y-intercept of 37,939. You can see we have a y-intercept right around 37,000. I mean, we're hitting here between 35,000 and 40,000. So this is a pretty good line that fits this data fairly well. So to end with this, again, as I've said before, one of the best things that we can do, or one of the more important things that we can do once we have the line of best fit, is we can use it to help us to predict other information. So let's use the equation for the line of best fit to predict a person's salary if they receive 7 years of education after college. So we don't have information on 7 years, right? We have 6 years and we have 10 years, but we don't have 7 years. So what we can do is we can use this equation. Now remember that our x values represent the number of years of education after high school. So we can substitute in for x7 into that equation that we just did, and see what value we get for y. And that will tell us approximately what a person's salary is, and it should fit fairly nicely on that line. So let's do that fairly nicely on the line. 37,939.199 plus 3,034.02 times 7 gives us a y value of 59,177 dollars, and because we're dealing with money, and 34 cents. So 59,000. Let's go up here and see if that makes sense. So when x is 7, is y around 59,000? So when x is 7, it'll be right around here. So when x is 7, and look at that. We get a y value, this is 50, there's 55, and that's 60. looks like we're fairly close to 60. We're in between 55 and 60,000, but remember that this line was an estimate that we just drew. So to answer this question, if we have if a person receives 7 years of education after college, based on this data and based on this regression equation that we just used, their salary would be $59,177.34. And that's it for linear regression. For linear regression, I want you to be able to approximate the line of best fit by drawing it. So approximate line of best fit. I would like for you to use the formula to find the line of best fit. And then I would like for you to be able to use that formula to help you to predict information. So once you have the formula for the line of best fit, use the formula to predict info. Okay, so this is it for linear regression. Thank you very much, and I will see everybody at the final exam review.